Hey everyone, welcome back to another video by Camroom 5. In the previous video, we had been talking about the concept of rate equations. We came across the concept of rate constant, which means a specific constant for each rate equation. And then we also talked about the idea of order, which was the exponent to which the concentrations were represented in a rate equation. Then we solved a calculation based question and we saw how orders are represented graphically. Like first order means rate doubles when concentration doubles, but second order means rate quadruples if the concentration doubles. Let's do one more question to see how things are interrelated. Like here, chlorate 1 ions are undergoing a reaction under aqueous conditions. I can see the concentrations of ClO minus and ammonia is given. So my rate equation will involve chlorate 1 ions with order A and ammonia with order B because both are unknown. My first instinct would be to compare experiment 1 and 2. But the problem is that chlorate and ammonia, both concentrations are changing. That's going to make things more complicated, right? So why don't I compare experiment 2 and 3? Because in 2, the concentration of chlorate is same as 3. So ammonia can be easily compared between experiment 2 and 3. So I will say compare experiment 2 and 3. And I can easily see that rate is also changing. Ammonia is doubled and rate is almost becoming 4 times. So I will say that rate in the third experiment over rate in the second experiment is proportional to ammonia in the third experiment. How will I write that? I will write ammonia in square bracket and then 3 ammonia in the third experiment over ammonia in the second experiment, so NH3 2. And then I will write the exponent of B because that's the order. 8.20 divided by 2.05, which is the rate, is proportional to the third concentration of ammonia divided by the second concentration of ammonia raised to the exponent B. When I solve it, I get to know that 4 is proportional to 2 raised to the power B. Now that is very obvious that exponent B is equal to 2. So actually the order of ammonia was 2 in my question. Now it is easier to compare experiment 1 and 2 because at least I am aware about ammonia. You can see between 1 and 2, both concentrations are changing, so don't forget to involve both. Let's do that. Now we are comparing experiment 1 and 2. I will write rate of second experiment R2 divided by rate of first experiment R1. It's proportional to the second and first concentration of ammonia. So NH3 second over NH3 first raised to the exponent square. Why? Because we have already solved it and we know that it's raised to the exponent square. Then we write chlorate in the second divided by chlorate in the first raised to the power A for apple because we don't know that. Now moving on. We put in the values to see how things are changing. The rate in the second was 2.05 and the first was 0.256. Ammonia was 0.2 in the second one and 0.1 in the first one, raised to the exponent square. While when we talk about the concentration of chlorate, the chlorate second was 0.4 and chlorate in the first case was 0.2, raised to the exponent A. Now we solve it, so we get to know that 8 times change in rate of reaction was proportional to 4 times change in the concentration change of ammonia because 2 ka square and then times 2 raised to the power A, which was the order of chlorate. 8 is proportional to 4 times 2 raised to the power A. We obviously know mathematically A has to be 1 because 8 is equal to 4 times 2. So 2 raised to the power A means 2 raised to the power 1. Here we get to know that exponent A, which is the order with respect to chlorate, is 1. Now we go back to our rate equation and we rewrite it. The way we rewrite it should involve both the orders. So here, rate, let's rewrite that. Rate is equal to k, which is the rate constant. So rate is equal to k, chlorate raised to the exponent of 1 and ammonia raised to the exponent of square. This equation shows us that order, now let's solve the units first. The unit is of rate of reaction is equal to mole per decimeter cube per second. Then K is written the way it is. Chlorate concentration was in mole per dm cube, ammonia concentration was also mole per dm cube, but ammonia concentration had a square on it. When we cancel out the unwanted stuff, both mole per dm cubes cancel out each other. 1 over second is equals to K mole per dm cube raised to the power square. When we make K the subject of the equation, K is equal to dm6 divided by mole square second inverse. So another way of writing that would have been K is equal to dm6 mole -2 second -1. So this is how we solve that. If we make a graph to show how the order can be represented, we put concentrations on the x-axis and rate on the y. Chlorate is directly proportional, but ammonia is exponentially related. And this is how we sum up orders and rate equations. We have 4 categories of orders. Rate can be related to x0, x1, x2 or pseudo order. If rate isn't related to x concentration, it's 0 order. When x doubles, rate doubles, that's order 1. If concentration of x doubles but rate quadruples, that's order 2. And finally, pseudo order means that x concentration was so much in excess that even if changing it is not detectable. So change in x concentration will not be affecting the rate because x is so much in excess that changing it from 99 to 98 will not have any effect on it, right? Now with this, let's move to another topic, which is order and reaction mechanism. This involves that if a reaction is multi-step reaction, then the rate of reaction, or you can say the rate equation, for a multi-step reaction is written only for one of those steps, which should be called the rate determining step. The rate determining step, or RDS, is one of those multi-steps, but it is the step which is the slowest step. So what's the definition of a rate determining step? It is basically the slowest step of a multi-step reaction. It can be step 1, it can be step 2, it can be step 3 of those reactions, but it is only one of them and it's the slowest step, and rate equation is only written for them. Like, consider these 3 steps for a reaction. The overall equation can be written by cancelling out same things from both sides. So when I cancel multiple ions, my overall equation can be written very simply. I will just write 2 cerium positive 4 ions and 1 Tl plus ion to give me 2 ions of Ce3 plus and 1 single ion of Tl3 plus. All the other ions got cancelled out. But now let's talk about RDS. If step 1 was the rate determining step, then rate equation should be written for step 1. Step 1 has Ce4 plus and manganese 2 plus. So rate is equals to rate constant Ce4 plus and Mn2 plus, both 1 times each, both raised to the exponent of 1, because both are involved 1 times each. Now here's what makes things complicated. If step 2 was your rate determining step, then consider step number 2. In step number 2, rate is equal to K, and what is there in step 2? we have a Ce4 plus, so I write that Ce4 plus. And then what else do I have? I have Mn3 plus. But Mn3 plus was made by step 1. It was a product of step 1. So I will go back to the reactants of step 1 because the reactants gave me Mn3 plus. So I won't write Mn3 plus, I will write all the reactants of the previous step which will be Mn2 plus and Ce4 plus. If your reactant was a product of previous step, then write those reactants. So I will double the Ce4 plus and I will write Mn2 plus 1 times. Let me write it more clearly. Yeah, Ce4 plus gets exponent 2 and Mn2 plus gets exponent 1. I know these things are requiring more practice. That is why I have also got another question. Let's consider these 3 steps. The overall equation can be written very easily. We cancel out the same stuff from both sides like the OH, like the HClO. And when I consider these, I get to know that overall equation is just ClO minus plus I minus gives you Cl minus and IO minus. Nothing big about it. But remember, this is not your rate equation, right? Rate equation is written for the RDS. So let's consider that if step 1 was your RDS. If step 1 is RDS, then put all the reactants of step 1. Let me remove these. The reactants of step 1 is ClO minus and H2O. So I will write ClO minus raised to the power 1 and H2O raised to the power 1. And that is very simple, right? So order with respect to ClO minus is 1 and order with respect to H2O is also 1. Things would be a little more complicated if second step was the rate determining step. Like for example, if second step was considered as RDS as rate determining step, let's put everything which is involved in second step. So I have I minus over there, I will write that. So I minus can be written with an exponent 1 because only 1 mole is involved. And then HClO. But HClO was made by the step 1. So please write all the reactants of step 1 instead of HClO itself, which will involve ClO minus and H2O. Because these were the reactants that gave you HClO. So order with respect to I minus is 1, order with respect to H2O is also 1, and order with respect to ClO minus is also 1. So if the third step was considered, we would do similar kind of equations and calculations. I hope we can see that if first step was RDS, it would be an overall second order, and if the second step was RDS, it would be overall third order reaction.